My name is Caleb Harris. This is my report for Lab 3 for Physics 2211. The purpose of the black hole lab was to find the mass of a black hole, the initial velocity of my spaceship, to get close enough to the black hole without crashing. The main physics principles are Newton's second law of motion, the position update formula, and the law of gravitational force equation and the impulse equation. The momentum equation, momentum equals mass times change of velocity, and the impulse equation, mass times change of velocity equals F net times delta t, tied directly to the kinematic equation, Vf is equal to V naught plus acceleration times time. Vf is the final velocity in meters per second, while V naught is the initial velocity, also in meters per second. A represents acceleration in meters per second squared, and t represents time in seconds. F net, which equals the derivative of momentum with respect to t, can be split into its parallel and perpendicular components. Perpendicular represents change of direction, while parallel represents change in the magnitude of velocity. The position update formula is final position is equal to initial position plus v average times delta t, and is used when net force is not constant, like in spring or orbit problems. Next is the gravitational formula, which is the gravitational constant times the mass of object 1 times the mass of object 2 all over the distance between the two objects squared. Finally, Newton's second law of motion also plays a role, which is represented by the equation F is equal to m times a. F is force in newtons and m is mass in kilograms. The main result of the lab was the mass of the black hole and initial velocity of the spaceship. The mass of the black hole is 1.16 times e to the 34th kilograms. The initial velocity of the spaceship is negative 15 e to the 6th in the x dimension and negative 7 e to the 6th meters per second in the y dimension. The black hole was a system in part 1, and its surroundings are everything else in the universe. The spaceship was a system in part 2, and its surroundings are everything else in the universe. The initial velocity of the black hole in part 1 is 0 in the x dimension, is 0 in the y dimension, and is 0 meters per second in the z dimension. The initial velocity of the spaceship is negative 15 e to the 6 meters per second in the x dimension, and negative 7 e to the 6 meters per second in the y dimension, and 0 meters per second in the z dimension. For part 1, I edited the initial final momentum, the changes in the velocity and momentum, and dp/dt. Next, I found dp/dt parallel to p hat, f net par, dp/dt perp, and f net perp. Finally, I use these values to calculate the mass of the black hole using the gravitational force and Newton's second law. In part 2, I used my calculated mass of 1.16 e to the 34th kilograms. Then I used the gravitational force to calculate net force on the planet and net force on the spaceship. I did this by first finding the radius, the unit vector of the radius, and by substituting values into the gravitational force equation. After, I summed all the forces acting on the ship and the planet. Finally, I used the position update and velocity update formula to find the final position and final velocity of the ship and planet. To get the initial velocities, I guessed and checked until I got a path that did not break. The main difference between the starter code and the edited code in part 2 is that the starter code spaceship crashes directly into the black hole. My edited spaceship avoids the black hole and follows this path. Other than this difference, my models were very similar to the starter codes. There is very little chance of possible error since this lab was purely computational. But in part 2, I could tweak the initial velocity of my spaceship so that the path of the spaceship is closer to the black hole. For the what-if question, there is no difference between the rate of change of the momentum and the net force. Net force is found by dividing change in momentum over change in time. By splitting the net force into its parallel and perpendicular components, I split the change in momentum over change in time into its perpendicular and parallel components. In all, they're the same thing. For the spaceship to stay in orbit around the black hole, the initial velocity in the y direction has to be less than my current y initial velocity. I do not have an actual value for the initial velocity, but this prediction would prevent my spaceship from overpowering the gravitational force of the black hole. My black hole mass is 1.6 e to the 34th kilograms, and the initial velocity of the spaceship is negative 15 e to the 6 meters per second in the x dimension, negative 7 e to the 6 meters per second in the y dimension, and 0 meters per second in the z dimension. The main models of the lab were Newton's second law of motion, impulse equation, and position update formula, and the gravitational formula.